One light year is about 9.46 trillion kilometers. That single number is enough to make every machine we have ever built look almost laughable. Nothing we have launched could cross it inside a human lifetime. Not even close. Take Voyager 1, the fastest thing we have flying. It has run without stopping since 1977, almost 50 years, at around 17 kilometers per second. And in all that time, it has not yet crossed even one light day. The distance light covers in a single day. It reaches that mark on the 18th of November, 2026. Half a century of flight for one day of light. Voyager 1 launched in 1977, and it has been coasting outward ever since, almost 50 years without a single stop. It moves at about 17 kilometers every second, roughly 61,000 kilometers per hour. Faster than nearly anything human hands have ever made. Nothing we have flown carries a person even close to that pace. And here is what that speed actually buys you. After almost half a century of flight, Voyager 1 is only now about to reach one light day. One light day is simply how far light travels in 24 hours. And the exact moment the probe crosses it falls on the 18th of November, 2026, about 25.9 billion kilometers from home. It will be the first thing we ever made to touch that mark. Sit with that for a second. Nearly a full human lifetime of travel at the highest speed we have ever sustained, to cover a single day of light. And the strangest part is that this messenger is dying. As of April 2026, NASA confirms both Voyager craft are still calling home, but they are losing roughly 4 watts of power every single year. The engineers have been switching off instruments one by one just to keep the rest alive. One of the science instruments went dark on the 17th of April, 2026, after nearly 49 years of running. One NASA engineer put it plainly, any day could be the last. So the same spacecraft that is about to touch its first day of light is also quietly running out of the power to tell us about it. That is the machine at the very front of our reach. One light day after 50 years, and its lights are going out. Before we go further into the dark, what part of the world are you watching from tonight? Drop your country in the comments. I love seeing how far this signal travels. So a full year of light, 365 days like that one. How long would that take? Before we answer, we have to clear away a trap, and it is hidden right there in the name. A light year is not a unit of time. It is a distance. It is the distance light travels in 1 year, and that distance is about 9.46 trillion kilometers. The word year is sitting inside the name, so our minds quietly assume it is some span of time we could wait out. It is not something you wait through, it is something you cross. And it helps to remember just how fast light is. In a single second, light could circle the Earth about 7.5 times. That same light, the fastest thing there is, needs a whole year to cover 9.46 trillion kilometers. Nothing in the universe moves quicker, and even it takes a year. Once you see that, the question changes shape entirely. Asking how long it takes to cross 1 light year is like asking how long it takes to cross a road. The answer depends completely on how you are moving. On foot, it is one thing; in a car, another. And at the speeds human beings can actually reach, the answer is about to become almost absurd. Here is one way to feel the size of that number. Imagine you could drive without ever stopping at a steady highway speed of about 100 kilometers per hour. To cover a single light year that way, you would need more than 10 million years behind the wheel. Light does it in 1 year. You would need an entire geological age. That is the gap we are working against. And it is why the honest answer to how long has nothing to do with patience and everything to do with speed. So let us stop imagining and use the real machines we have flown. 3 of them, 3 speeds, 3 numbers. And each one sounds more ridiculous than the last. Start again with Voyager 1 at about 17 kilometers per second. It is the fastest object ever to leave our solar system, and at that pace, 1 light year would take it around 17,000 years. Try to hold that against a human timescale. 17,000 years is roughly the stretch from the first paintings on cave walls to this very moment. The whole arc of art, cities, empires, everything, just to cross a single year of light. Now push harder. The Parker Solar Probe is the fastest thing our species has ever built. Diving close to the sun, it hit a top speed of about 692,000 kilometers per hour on the 24th of December, 2024. That is around 192 kilometers per second, and as of now, nothing has beaten it. Yet even at that record pace, 1 light year would still take about 430 years. A ship that left in the age of Shakespeare would only be arriving around now. Then there is the wild card, Breakthrough Starshot, not a spacecraft that exists, but an idea, firing giant lasers at a tiny sail to push it up to 20% the speed of light. At that speed, 1 light year takes only about 5 years. But there is a catch that changes everything. Starshot only works for something the size of a postage stamp, a chip that weighs a few grams carrying no people at all. The moment you add mass, a crew, life support, and the need to slow down at the far end, the real speed collapses back toward a fraction of that. It was always a concept more than a plan, and even that concept may have quietly faded away. So look at what we found. The whole history of space travel, from the crudest probe to the boldest dream, fits between those 2 poles. 17,000 years and 5. And here is the quiet lesson inside the numbers. Parker is about 11 times faster than Voyager, yet all that speed only drags the number from 17,000 years down to a few hundred. Still longer than any empire we have ever built. The problem was never that we are slow. The distance simply belongs to a different scale of measurement altogether. Faster does not fix it. And there is a second problem hidden underneath the first, because reaching a speed is only half of it. How do you ever stop? Hold that question. We will have to come back to it. If you think this video deserves more attention, please click the hype button below. Each hype will help this video get recommended more often. But before we can even worry about stopping, there is a problem that comes much sooner. The problem of starting. Just to break free of Earth's grip, a rocket has to reach what we call escape velocity, about 11.2 kilometers per second. That is faster than a bullet leaving a gun, and that only gets you off the porch. Because reaching escape velocity still does not put you out there. The first few million kilometers are a struggle, since the sun's gravity keeps pulling on everything nearby. It took the Voyager probes decades just to pass the outer planets. Leaving is not a single push. It is a long, uphill climb. Picture it like climbing out of an enormous well. The closer you are to the bottom, close to the sun, close to a planet, the more strength every step costs you. And even when you finally haul yourself up to the rim, you look out and see nothing but desert stretching to the horizon. Getting to the edge is the easy part. What lies past it is the real distance. And the deeper truth is how vast the energy gap really is. To push any real mass up to even a small fraction of the speed of light is beyond every propulsion system we have. Not by a little, but by many orders of magnitude. Chemical rockets, the kind that put us into space, are essentially useless for this. Even the most efficient ion engines we have built would need decades just to gather up enough speed. We are not a little short. We are short by factors so large they are hard to picture. So suppose we solved all of that. Suppose we reached the speed we dream of. That is exactly when a new problem appears. One almost no one thinks about until it is too late. This is the question we promise to come back to. Reaching interstellar speed is only half of the puzzle. If you actually want to arrive somewhere, to stop at your destination instead of tearing past it and vanishing forever, you have to slow down. And in principle, slowing down takes nearly as much energy as speeding up. There are no brakes in a vacuum, no air to push against, no road to grip, nothing to hold on to. You cannot simply let go and drift to a halt. This is exactly why the Starshot idea sidesteps the whole thing by giving up on stopping. The tiny sail probes would only flash past a distant star in a matter of hours, snap a few images, and race on into the dark, lost for good. To actually stop and stay, you would have to carry a whole braking system, and that extra mass breaks the entire calculation. The moment you want to arrive rather than pass by, the dream gets far heavier. Think of it this way. Throwing a ball as fast as you possibly can is easy. But now, catch that same ball gently at the far end of a stadium, cupping it to a perfect stop in your open hand, with nothing to slow its flight along the way. That is the part that borders on impossible. Going fast is the easy half. Coming to rest is where physics stops cooperating. Now, scientists have actually proposed a way to brake without fuel, a magnetic sail. Picture a vast loop of superconducting wire, using its magnetic field to push against the thin gas between the stars and drag the ship down. It is clever, but it only works well at very high speeds, and it would still need decades to bring a ship to a stop. Worse, that same enormous loop of wire is fragile, horribly easy to damage when it strikes interstellar dust. Every escape hatch opens onto a new trap. If this journey is bending your mind as much as it bends mine, tap the like button. It genuinely helps more curious people find this. And that word, dust, turns out to matter far more than it should. Because out there, at these speeds, even the emptiness is not safe. But first, understand what that emptiness actually is. Because the real problem was never the distance itself. It is what sits in between, which is almost nothing at all. The space between the stars is so empty that a single cubic centimeter of it holds, on average, only about 1/10 of one atom. Not 1/10 of a gram, 1/10 of a single atom. That is a level of nothing our instruments can barely reproduce. And that is the strange part of the journey. You would fly for years while the view outside your window barely changed. No planets sliding by, no landscapes, no events. Just a scattering of stars shifting so slowly that decades could pass before you saw any of them move. It is not a road with scenery. It is a room with the walls painted the same black in every direction, which is why the old picture is wrong. The solar system is not a harbor you sail away from. It is more like an island. One small patch of warmth and light, surrounded by an ocean so wide and so empty that the human mind quietly refuses to hold it. We are not standing on a shore looking at the next shore. We are standing on the only land there is. Let that sink in further. The space between stars is a better vacuum than the finest one we can build in any laboratory on Earth. Gather every scrap of matter in a stretch of it the size of a building, and you might not have enough to see with your naked eye. That emptiness is not the gap between destinations. It is the destination. The nothing is the thing you have to cross. And crossing nothing, it turns out, is the hardest journey of all. And here is the cruel twist. Because space is nearly empty, collisions are almost impossibly rare. You could fly for years and hit nothing. But at the speeds we would need, that almost nothing turns deadly. Every speck of dust, every stray atom you meet at a staggering velocity. And it carries an enormous amount of energy when it strikes. Push past about half the speed of light, and the ordinary hydrogen atoms drifting in your path slam into the ship like hard, ionizing radiation. Tens of millions of electron volts each. Now put a number on it. At 20% the speed of light, about 60,000 kilometers per second, a single grain of dust hits with the energy of moving mass wound up tight. A dust mote too small to see, striking at that speed, can release energy on the order of a hand grenade from one invisible speck. And at the most extreme speeds, physicists estimate a single cosmic dust grain could carry the punch of tens of kilograms of high explosive, a thing you could not even find with a microscope. There is no planet's magnetic field out there to shield you either. Cosmic radiation pours through every living cell year after year, and we have no practical shielding that can hold up against it over a journey that long. The emptiness does not protect you, it exposes you. Think of standing still while a single snowflake drifts down, harmless, weightless. Now drive into that same snowflake at 200 kilometers per hour, and it cracks against your windshield like flung gravel. Speed turns the harmless into the lethal. The snowflake did not change, only your velocity did. To make this real, the scientists behind Starshot ran the math. For one of those tiny gram-scale sail probes to survive the dust at 20% light speed, they calculated it would need a shield of graphite 1 to 3 millimeters thick. Otherwise, the dust would melt the surface away. A typical dust grain weighs only about 3/10,000ths of a trillionth of a gram, and still the ship must wear armor. A craft thinner than a sheet of paper, forced into a suit of armor just to survive flecks of dust it cannot see. And that is the paradox that should stay with you. At these speeds, the universe being empty is not enough to spare us. The thinnest, most fragile nothing imaginable still carries enough force to tear a ship apart. The one place with nothing to crash into becomes the one place where everything can kill you. If that sounds insane to you, a grain of dust hitting like a grenade, type the number 7 below and stay with me. Because what happens to time on that ship is stranger still. But suppose the ship survives all of it. There is a stranger question waiting, a gentler one. For the person inside, how long does this journey actually last? Because time itself does not behave the way we expect. Near the speed of light, time slows down for whoever is moving. The physics of it follows a simple factor: the square root of 1 minus your speed squared over the speed of light squared. In plain terms, the faster you go, the slower your own clock ticks compared to the ones you left behind. At around 70% the speed of light, a traveler's clock runs about 30% slower than ours. A voyage that Earth measures in many years would feel meaningfully shorter to the person living it on the ship. Not instant, not a single year, but genuinely less. This is the famous twin paradox. One twin stays home and ages normally. The other flies out at tremendous speed and comes back younger than the sibling they left behind. And this is not science fiction, and it is not a thought experiment we merely hope is true. It has been measured with atomic clocks flown on aircraft and in the stretched lifespans of tiny particles called muons that survive longer when they move near light speed. In fact, we know it because we have measured it directly. Back in 1971, an experiment flew atomic clocks around the world on ordinary commercial planes. And when they landed, they were off by exactly the few billionths of a second relativity predicted. And the GPS in your phone has to correct for time dilation every single day, or your location would drift off by kilometers within hours. You are already living inside this effect. It runs quietly under the maps in your pocket. But there is a quiet cost folded into that gift. For the traveler, the distance seems to shrink, yet the price is a loneliness that is nearly total. They come home younger, yes, but everyone they loved has aged or is already gone. The universe hands you more time and then takes away every single person you might have wanted to share it with. You keep your years. You lose your world. And here is the harder truth. Almost no crewed ship could ever reach 70% the speed of light. If we cannot go fast, only one option is left. We go slow. We build a generation ship, a city of metal where people are born, live out their whole lives, and die, passing the mission down to their children across thousands of years. On paper, it is a beautiful idea. In reality, it runs it to a limit that is not about engineering at all. It is about us. Over 1,000 years, a language can drift so far that no one could understand its earliest speakers. Culture shifts. The memory of Earth would slowly fade. After enough generations, the children born on that ship might no longer know what Earth was. To them, the whole universe could be nothing but metal corridors and a story their grandparents told. This is not a certainty, only a possibility, but it is the possibility that unsettles people most. The journey might succeed and still lose the very thing it set out to carry. There are other imagined ways around it: hypersleep, freezing the crew for the long dark, or sending robots and artificial minds in place of fragile human bodies. But both of them quietly change the question. They stop asking how a human being reaches another star and start asking whether the thing that arrives is still us at all. And scientists have actually tried to put a number on the human side of this. Using a simulation called Heritage, the astrophysicist Frédéric Marin at the Strasbourg Observatory calculated the smallest crew you would need for a voyage of roughly 6,300 years. The goal: to arrive with a full chance of success, without the crew collapsing from inbreeding. The answer was at least 98 people, plus a frozen bank of embryos to keep the gene pool healthy. Think about what that really describes. Not a spacecraft, a tiny society, designed so it will not tear itself apart over 6,000 years in the dark. The machine turned out to be the easy part. Keeping people human for that long is the real engineering. If that just gave you chills, share this with someone who would feel it too. And even if they make it, even if that small society survives the whole crossing, one last quiet fact makes the journey feel almost unbearable: the silence. Even from the edge of our own solar system, a radio signal already takes hours to crawl back to Earth. At a distance of 1 light year, by definition, a one-way message takes at least a full year to arrive. A conversation as we know it simply stops being possible. There is no back and forth. There is only sending and waiting. Picture what that means. You send home a single sentence: "We made it, we are safe," and wait a whole year before any reply could even begin its journey back. Every exchange stretches across a whole growing season. That is not just being far away, that is being cut off. And when you finally arrive, the sky itself barely reacts. Over the entire crossing of 1 light year, the familiar constellations shift almost imperceptibly. The patterns you grew up with look nearly the same the whole way. Only the star ahead slowly brightens. Behind you, the sun fades into one more point of light, lost among thousands, until you could no longer pick out home if you tried. We do not have to imagine this delay. We are living it right now. At this moment, a signal from Voyager 1 takes about 23 hours to reach us. Almost a full day for a single message, one way. Stretch that out to a full light year, and 23 hours becomes a year in each direction. This is not a theory on a page. It is the quiet gap we already live with, every time we speak to the most distant thing we have ever made. Which brings us to the part that is almost impossible to believe. Because after all of that, after crossing an entire year of light, we still have not really left home. Here is the turn that changes everything. Cross a full light year, and you may still be inside the gravitational reach of your own sun. The outer edge of the Oort cloud, The true gravitational border of our star, the last place where the sun still holds sway, is thought to lie as far as about 1.6 light-years away. Some estimates push it out toward 2, which means the first entire light year of your journey never even leaves the sun's backyard. We did not see that edge with our own eyes. It is far too faint and far too distant for that. We know it is there the way you know a country exists from the letters that arrive from it. Long-period comets come falling in toward us from every direction, out of that vast unseen shell, like mail from a border we have never once touched. And this bends the whole picture out of shape. The thing that sounded like an unimaginable distance, 1 light-year, turns out, on the scale of the galaxy, to be barely the first step out the door. And that smallest first step into the galaxy is already beyond our reach. The answer to how long it turns out says more about what we are than about how far it is. We have not even swum out past the shallows around our own island. And it is not because we lack the courage. It is because this ocean is simply larger than courage, larger than anything a body or a lifetime was built to hold. It leaves you with a strange choice to sit with. If you could be handed just one impossible technology, which would you take? A way to reach a fraction of the speed of light, or a way to keep human beings alive and whole across many generations? The speed or the survival? There is no obvious answer, and the reasoning cuts both ways. Tell me which you would choose down in the comments. I read them. And if a single light year cannot even carry us out of our own yard, look at how small that yard is against the whole house. Proxima Centauri, the nearest star to our own, sits about 4.2 light-years away. Cross 1 full light year, and you still have not covered even a quarter of the way to our closest neighbor. And Proxima is the lucky case. Most of the stars scattered across the night sky lie 10, 50, 100 light-years off. Now widen the frame all the way. The Milky Way stretches more than 100,000 light-years across. Against that, a single light-year carries almost no weight at all. It is not really a meaningful number on the scale of a galaxy. Put it back into a human life to feel it. Launch today at Voyager's speed, and to finish that 1 light-year, it would not be you or your children. It would be the children of your children's children across roughly 600 generations who finally arrive. And even then, Proxima would still be more than 4 times farther on. The galaxy is not a place we have not visited yet. It is built on a scale the human body was never designed to touch. And yet, hold both of these at once. One light year is enough to push every technology we own to its absolute limit, in energy, in time, in what a body can endure. And against the rest of the universe, that very same distance is almost nothing. Both things are true in the same breath. And that is not a thing to fear. That is a thing of wonder. If you find this content valuable, please give the video a hype. It's the simplest way to support the channel so we can continue making more videos like this. So this is where the answer finally lands. The truth is that even the smallest first step into the wider universe sits, for now, almost entirely beyond our reach. And there is something staggering in that. Not staggering in a way that should crush you. staggering in a way that shows you clearly exactly where you are standing. And where we are standing is on an island. If we are stuck here, on this one small world, that is not a sentence handed down to us. It is a reason to take care of the place. There is no other shore waiting out in the dark. There is only here. So the only sane thing to do is to look after here. There is a strange comfort in that, and the ship we began with can show it to you. On the 14th of February 1990, from about 6 billion kilometers away, Voyager 1 turned its camera back around and photographed the Earth. In that image, our entire world was smaller than a single pixel, a pale blue dot. Carl Sagan looked at it and wrote that this dot was home, everything we have ever known. It was, in his words, the only home we've ever known. The farthest traveler we ever built ended up teaching us the opposite of what it set out to find. Not about the places we might someday reach, but about the one place we already have and must not lose. Maybe that is the real thing a light year has to teach us. Not how small we are, but how rare this place is. The universe is almost endlessly vast. Home is the one thing there is only one of. If a journey like this one is worth stopping to sit with, subscribe and come with us, we will keep going out into the dark together, one quiet story at a time.